Hello, welcome to a continuation of section 11.2. We are going to dive into a couple topics here that I knew we weren't going to have time to do during class, but that I believe are pretty straightforward, and this should hopefully be a pretty easy video for you to kind of get through these topics. So the first one is parallel vectors. Now, you may remember how to do this in 2D. If you don't, it's going to make so much sense. Now, in 3 dimensions, when we're in R3, we have, our vectors in space. It's going to look a little bit different. So let's just start with in R2 here. If we are trying to find, and I'll just kind of notate this as, slope, that's the idea. Parallels, they have the same slope, right? So we can find the slope of u, and slope is rise over run. It's change in y over change in x. And so this pretty easy right there. Our slope is 4/3. And then we can do the exact same thing over here for vector v. Change in y over change in x, 12 over 9 is also equal to 4/3. So if we remember parallel lines, then parallel vectors in 2 dimensions have the same property. This only works in R2, so I'm going to write that off to the side here. So this is only applicable when we are in R2, because things are a little different when we get to 3 dimensions. But let me just go ahead and specify here that in 2 dimensions, our parallel vectors will have the same slope. Okay. And then we could also look at the fact that what we did here was we reduced, okay? So this is going to kind of bring us into 3D. Right here, my change in y over change in x did happen to be the exact same thing as the first vector because I reduced it. So another way that you could look at this is you could say that because vector v is a scalar multiple, it's 3 times vector u. Because this is the case, then we have parallel vectors.
I didn't
that.
understand
Okay. All right. If you ever hear my watch or devices just start talking, I don't know what the deal is, but apparently my devices think I'm always talking to them. So sorry for that little background noise. In R3, we can actually apply the second property. So only in R2 does this first one work. However, in R3, this second property will also apply. So let's just go ahead and take a look at that. When we go ahead and try and identify if we have scalar multiples, we are comparing the change in x from one to the other, the change in y from one to the other, and the change in z from one to the other to determine if one is a scalar multiple. And you can probably see here, but we'll just use the same idea of reducing. So does the change in x's, that ratio between the two, equal the same thing as the ratio between the y's here? Does that also equal the same thing as the ratio with our change in z's? Okay. Now, given that they all reduce to the same thing, which is a -3/2, then that means that yes. Okay, so for this one, yes. -3/2 times vector u is equal to vector v. And since they are scalar multiples, since we can write this statement here, so we can conclude that vector u is parallel to vector v. Okay, so if we're in 2D, it's just this basic idea of slope. When we are talking in more than 2 dimensions here, in this case 3 dimensions, we are looking for scalar multiples of one another. All right, so that's kind of easy topic number 1. Easy topic number 2 is really just a review of all of these operations that we've learned how to do with vectors. So I thought if you want to pause here, that you can do that really quick and try and answer all 4 of these questions. And then you can come back, play the video, and see if you got those right. So if that's the case, go ahead and pause here. All right, so if you did that, then we're going to just go through some answers. You can see how you're doing with all of that. And again, this is just quick, easy review. In component form, we remember that we are taking the terminal point and we are subtracting the initial point. And so for our purposes here, our initial point is P, our terminal point is Q, which means we are looking for vector PQ. That is very important how we label that. We always start with the initial point and go through the terminal point, and so we label them in that way. Now, if we do the subtraction here, and terminal minus initial, we would get 5 for our x coordinate, and we would get 4 for the y coordinate. So then we want to describe that using magnitude and direction. So if we remember how to find magnitude, that was the formula that we said essentially is Pythagorean theorem once you get this into component form. So we are taking the square root of 5 squared plus 4 squared, which gives us the square root of 41 for the magnitude. If you remember from the previous video, in order to find the direction angle theta, we are going to be taking the arctan of y over x. So 4 over 5. Doesn't lie on an easy angle on our unit circle, so we would need a calculator for that one. And if we do that, we get about 38.65 degrees for our direction angle. Now remember, that's coming off of the positive x-axis. And we know that that is in fact correct to keep that as a 38.65 degree direction angle because we know we should be in the first quadrant. Now, if you had a vector in component form in the second quadrant and you got 38.65, we would call that then a reference angle, and that would be from the negative x-axis. So you would have to figure out, okay, this angle is a reference. It's describing the distance from the x-axis. So I'd have to figure out what that angle is, that obtuse angle is in quadrant 2, just as a heads up there. If I want to write this in polar form, we simply can just describe this as being a scalar multiple of the magnitude that gets multiplied by the cosine of theta. So cosine of 38.65 degrees, comma, the sine of theta. Now, we could multiply that through and simplify, but as I stated before, that is a perfectly acceptable answer to leave in that form right there. And then we want to find the unit vector that's going in the same direction as PQ. And if you remember how we do that from the video, in order to find a unit vector, we want to take any magnitude that this vector V has, or in our case PQ. We want to divide that away from the vector so that we're left with a magnitude of 1. So we could leave this as 1 over the square root of 41 times vector PQ, which is 5, 4. And again, you could do this to varying levels of simplification. So you could say that this is 5 over root 41, 4 over root 41. You could rationalize the denominator to get the radical out of there, but again, you don't have to. One last thing, and this is just a quick heads up, spheres in 3 dimensions. If you remember circles in 2 dimensions, we used our center HK and we used our radius R. And what we did was we used H and K to kind of describe that translation in the XY plane. So a circle in 2D looked like x minus h squared plus y minus k squared is equal to our radius r squared. In 3D, we do have that additional z component. And so instead of using, h and k to represent our center, we make things a little bit easier on ourselves. And we just end up using x's and y's, and then we introduce that z component as well. So our formula here would be x minus x sub 1 squared plus y minus y sub 1 squared plus z minus z sub 1 squared is equal to r squared. So you just have this additional z component. Instead of choosing to go with different variables, we use x1, y1, z1 to represent our center. Okay, so hopefully, again, that was a pretty straightforward and, some easy things as you're thinking about your homework. As always, let me know if you have questions. I'm here for you, and I hope you have a wonderful day.